Dear students, in this video we are going to discuss about introduction to high voltage direct current transmission and early discoveries in transmission systems. So at the end of this video you will be able to know the basics about HVDC transmission systems and how the transmission started from AC and why it has converted to DC, and we will be discussing about the early discoveries of the transmission systems, how initially the transmission started, and from where the DC transmission came into the picture, and how the AC to DC transmission transfer take place. And we will be discussing about the importance of HVDC transmission system and how the HVDC transmission is achieved. So let us start with the video. So to start with importance of HVDC in transmission. So students, we know growth of any nation relies on the increased consumption of energy, especially what we call it as the electrical energy. And we know that electrical energy is generated in the faraway generating stations. Generating stations are not near the load centers or the consumers. We know even if you see in your locality, you will not be able to finding out any generating stations. Generating stations will be very far away, a minimum of 50 to 100 kilometers from the load centers. So the first challenge started with the transmission of these generating stations. And we know that the electrical energy consumption is increasing. The demand is increasing threefolds, fourfolds every year, because we have started using the many new electrical appliances and like air conditioners and all the other thing. So the electricity demand keeps on increasing. So the challenge of transmission of large amount of electricity which is matching the demand is one of the important aspect. So remote generation and system interconnection lead to a search for efficient power transmission at increasing power levels. And you know already that you might have studied in your previous courses that we cannot generate the power at higher levels of voltage. We will be able to generate only in 11 kV, 33 kV, like that. And we cannot just like the transmit it as it is. We need to step up the voltage. So for stepping up the voltage we should use transformers. For with the help of generating station transformers, we'll be stepping up the voltage, and stepped up voltage will be transmitted. The power will be transmitted for a long distance through AC transmission lines, and it will reach to a substation. And in the substation again it will be stepped down. The voltage will be stepped down, and again it will be transmitted for secondary transmission will takes place, and it will reach to the nearest substation of the consumer. From there the nearest transformer of the consumer. That goes on like that. Use things you know in terms of AC. So, but increasing the voltage is not always feasible as it involves various challenges. Generating stations generate in AC, that we know, alternating current. Increasing the voltage level of AC resulted in many problems, which led to the development of DC transmission for long distance transmission. So, why I am using the word DC transmission for long distance transmission? Because the transmission, when it is for shorter distance, we cannot rely only on DC, because the initial cost and all the other factors are comparatively very much higher. So we need to rely on DC transmission for long distance transmission only. We'll be discussing about this later in the forthcoming videos. And next slide, we are going to discuss about how this HVDC transmission is achieved. So this HVDC transmission is achieved with the help of two stations, which we call as sending end stations and receiving end stations. As we have already discussed in the previous slide, the electricity is generated in AC. It needs to be converted into DC for the DC transmission purpose. So that is what we have mentioned here. DC transmission requires conversion from AC to DC at the two places. One is at the sending end, another one is at the receiving end. So at the sending end, the AC voltage is converted into DC voltage suitable for high voltage transmission by using a converter station, which we call it as a rectifier station. At the receiving end, the DC voltage is again converted back to AC voltage by using inverter stations. We know that the receiving end always we need the power to be in AC, because the electricity majority of the consumers are using only AC, so we need the power back in AC. And one important factors is that this sending end rectifier station and receiving end interconverter station, both of them are interconvertible. That means that I can change this rectifier station into inverter station, and I can change this receiving end inverter station into rectifier station. So that means that I can send power from sending end to receiving end, as well as from the receiving end to the sending end. So back to back power supply is possible. Power reversible is possible only in HVDC transmission, not in HVAC, that is high voltage AC transmission. This is one of the important advantage of HVDC transmission systems. So this picture will give you a clear idea of how HVDC transmission works. So this is a general conventional thermal power generation and wind power generation. The power generated will reach to the sending end station. So this is what we call it as sending end station. The sending end station, what happens? It is a rectifier station. So it converts the AC into DC. And the converted DC voltage will be sent to the HVDC transmission lines, and it will be transmitting to the receiving end station. So this receiving end station again is converting this DC voltage into AC voltage, and remaining parts is as it is, like AC substations, as usual, the AC transmission line, and finally it will reach to the consumer. So these three parts only comprises, that is the rectifier station, the HVDC transmission lines, and the inverter station. These three parts completely comprises the HVDC transmission system. So these three parts are very important factors in the HVDC transmission systems. So students, hope you might have understood how the HVDC transmission is achieved in the transmission of electrical power supply. So let us continue with the early discoveries in transmission systems. We know initially the electrical science and all the discoveries have taken place only with the DC, and later on AC came into the picture. All the discoveries, like discoveries by Galvani, Volta, Orsted, Ampere, everyone started with their current only. And later it is improved in alternative current based on its advantages. And you can see in 1870 commercial use of electricity started, carbon arc lamps, and 1882 the first electric power system by Thomas Alva Edison in the New York DC system for 59 consumers for a voltage level of 110 volt underground cable with incandescent lamp load started. In 1884 electric motors were developed by Frank Sprague, and in 1880s this is the advent of transformers, polyphase circuits, and induction motors. So transformers and polyphase circuits, induction motors started a new revolution where the increase in voltage is possible and all the transmission of supply is possible. So this is one of the important phase of the transmission where the transformers are started to develop. And in 1880 to 1911, the first high voltage direct current transmission developed by Thuri, which we call it as Thuri systems, are installed with an voltage level of 57.6 kilovolt and maximum circuit voltage reached up to 125 kilovolt. But this system has been dismantled in 1937 after the death of the scientist Thuri. So it was of no use. After that, the DC transmission again it stopped. There was no development in DC. In 1891, first transmission of three-phase alternating current using high voltage took place in 1891 during the International Electricity Exhibition in Frankfurt. In 1893, the Niagara Falls Power Company awarded the Westinghouse a contract to harness the power from Niagara Falls and deliver it to Buffalo, New York, 22 miles away using a new AC technology. So all these developments are in terms of AC transmission. In 1939, demonstration of first DC transmission using grid-controlled steel tank mercury arc conversion given in Switzerland for a distance of 30 km. In 1954, this was the first milestone of HVDC transmission, where the first commercial HVDC transmission of 20 megawatt 100 kilovolt from Swedish mainland to the island of Gotland through single conductor cable with return path through the sea and earth. This is one of the important advantage of the HVDC system where we can use only single conductor cable and use the sea and earth as the return path, which is not at all possible in terms of an AC system. So we will have a separate video on the difference between comparison between AC and DC transmission. In that we will discuss all these things in detail. And next is the 1962 to 65. We have started full scale overhead line covering a distance of 474 kilometer plus or minus 400 kV, 720 megawatt at Volgograd. So this development started to come when HVDC transmission came into the picture. So these are all the global scenarios. After 1965, it started increasing. So ever all through the world, the HVDC transmission systems have started their work, and they are developing in each and every parts. And next comes the development and transmission system in the Indian scenario. In Indian scenario, the Electricity Supply Act started in the year 1948, and in 1950 to 60, growth of state grids. So in India, currently we have only one grid, one nation, one grid. But previously we had regional grids like southern grid, northern grid, northeastern grid, western grid, and eastern grid. So totally we had five grids. So these five grids are interconnected only because of this HVDC systems. So HVDC links played a vital role in the interconnection of these regional grids, and the making the very big challenge of one nation one grid plan. Okay, so initially we have started with state grids, and the state grids are developed to regional grids in 1965 to 73. And in 1977, introduction of 400 kilovolt voltage level started for transmission. In 1989, we have started the development of HVDC back-to-back system. In 1980 to 88, the growth of regional grid systems as associated transmission system with central sector generation started. In 1992, the first interconnection started. The eastern region and the northeastern region were synchronously interconnected through Birpara Salakatti 220 kV double circuit line. So in 1990, the introduction of HVDC bipole line started, and in 2000, interconnection of 765 kV transmission line it was initially charged at 400 kV started. So this is what I have discussed with students. The eastern region is connected to the northeastern region. So when we are interconnecting the grids, I mean the regional grids, it is very important for us. So initially there was huge surplus power generated in one grid, and there was a huge deficit on the other grid, but we cannot transfer the power because of the demands, because of the interconnection problems, frequency issues, all these things. HVDC solved all those issues, and in 1999, transmission planning reoriented towards all India system. This is where we have started the all India grid plan in 1999. So in 2003, Electricity Act 2003 was enacted, and ABT with real-time settlement mechanism implemented in all the five electrical regions, creating the basic infrastructure for the operation of an electricity market. And in 2003, again, one more interconnection took place. The western region was connected, interconnected to the eastern region, the northeastern region system synchronously through 400 kV Rourkela Raipur double circuit line. And thus the central India system consisting of eastern region, northeastern region, and western region came into operation. And then we have started bulk interregional HVDC transmission system, that is Talcher Kolar HVDC link, which is of power rating 2000 megawatt. 2004, we have started the open access in transmission. In 2006, next important interconnection took place, synchronous interconnection with northern region with eastern region, northeastern region, and western region system to the formation of new grid. New grid refers to northern, eastern, and western region grid with the commissioning of Muzaffarpur Gorakhpur 400 kV double circuit line. The northern region also got interconnected to the system, making an upper India system having complete system like northern region, western region, eastern region, and northeastern region. So in this, we can see in the previous case, we have seen that the western regions was interconnected to eastern region, northeastern region system. It is not, that does not mean that western region is directly connected to eastern region and western region is directly connected to the northeastern region. So initially it started with the interconnection of the system, and later they will have one more interconnection from western region to eastern region directly and western region to northeastern region directly. So one more HVDC links we will be using. If that is the case, then we can transfer the power separately between eastern region and western region, and separate power transfer is possible between northeastern region and western region. Hope these things are easily understandable for you. And in 2007, the northern region also synchronously interconnected with western region through Agra Gwalior 765 kV single circuit line operated at 400 kV levels, besides the interconnection of northern region and eastern region. The 765 kV operation of Sipper substation started in 2007, and 765 kV operation of 765 kV transmission lines. So you can see initially here the 765 kV line was there, but they were using at the level of 400 kV level. And in 2007, by the end of the 2007, all the 765 kV lines are have charged for 765 kilovolt. So you can see in 2007, the North new grid operation, new grid was formed. 2006, 2007, new grid was formed. That means the complete northern region was interconnected. Only region which was left out is the southern region. Northern region, western region, eastern region, and northeastern region are interconnected. But only thing which was left out is southern region. It took them 7 years around. About 2014 only, the southern grid is synchronously connected with the rest of all India grid. Still 2014 it was like rest of India grid and southern grid, because practically they have faced many problems in the interconnection of the southern grid with the rest of India grid. Many news came at that time, like there was a large interconnection issues, there are frequency nominal frequencies of great difference, and it resulted in major tripping problems, fault issues, all those things came. So they have tried about some 7 years, and finally they have achieved in the year 2014 the southern grid synchronously connected with rest of all India grid in December 2014 through the single circuit 765 kV Raichur Solapur line. In 2016, Northeastern Region Grid directly connected with Northern Region Grid, the longest 600 megawatt HVDC line plus or minus 800 kV from Bishwant Chariali to Northeastern Region to Agra in Northern Region for dispersal of power from Northeastern Region to Northern Region or Western Region was possible. In 2017, 765 kV double circuit Nizamabad Hyderabad commissioned in July, and plus 800 kV Champa Kurukshetra HVDC bipole commissioned in September, and 800 kV Alipurdar Agra HVDC bipole commissioned in September again. In 2018, 765 kV Jabalpur Orai Aligarh double circuit system commissioned in March, and 2019 world's longest HVDC link. The first unit is flagged off. If this project completes, that time we will be having one of the world's longest HVDC link, which is of about 1,830 kilometer, which is from Raigarh to Pugalur, 800 kV ultra high voltage direct current system. So students, you might think, what is the need for knowing all these things? When I'm studying HVDC systems, why should I know about the Indian scenario? Why should I know about this early discoveries in transmission systems in the Indian scenario or global scenario? All those things. The reason behind this that when we are knowing what is the purpose of HVDC transmission system, and we will be easily understanding the technical details of the HVDC transmission systems. In the next videos, I'll be discussing about the comparison between AC and DC transmission, where I'll be using DC transmission. Why not I can't use AC transmission systems in terms of the technical things. But when it comes for the real-time applications, so these are the real-time applications. These HVDC links helped the achievement of One India, One Grid. And till date, we are using this for the One India, One Grid. And One India, One Grid was achieved only because of the HVDC transmission systems, because till a longer time we were using the regional grids. Because of the regional grids, there was a huge power demand in one region, and there was a huge power surplus in one region. It was wasted. Now you can generate in Maharashtra, and you can transfer the power surplus power to West Bengal, and if there is any surplus power in West Bengal, it can be transferred to Kerala or Tamil Nadu, anywhere. So One India, One Grid system helped a lot in the effective usage of the electricity, because in one region the probability of getting a large power is possible, in one region it is not possible. So all these things helped a lot, and HVDC played a vital role. And students, you can refer to this website powerministry.nic.in, where you will get authentic details of both the Indian generation, transmission, and distribution systems. Being an electrical engineers, we should know what is the recent developments in our field. Every company and every organization expects that we should be updated in our field at least. So you regularly follow up with this website, you will be getting all the recent developments in the power ministry and the electricity supply, and what are all the milestones that we are reaching, we will be getting. If you know all these things, it will be very helpful for you in future. So let us discuss the next slide, the milestones in HVDC transmission system. So when we started with HVDC transmission system, we have already discussed what are all the components that we should need. So we need a rectifier, we need an inverter, and we need transmission line, sending and station, receiving and station. When we are converting AC to DC, we should have some filters to smooth out the waveform because we need to have a straight line waveform. So all these factors played an important role in these milestones. So in 1901, Hewitt's mercury vapor rectifier was developed. In 1940s, experiments with thyrotrons in USA and mercury arc valves in Europe started. In 1954, which was the milestone discussed already, first commercial HVDC transmission started. In 1970, solid-state semiconductor valves were developed. In 1979, first microcomputer-based control equipment for HVDC started. And 1984, highest DC transmission plus or minus 600 kilovolt in Brazil. It started, and in that time it was highest. Now it has moved more even plus or minus 800 kilovolt. In 1994, first active DC filter was developed. In 1998, first capacitor commutated converter in Argentina Brazil interconnection. In 1999, first voltage source converter for transmission in Gotland and Sweden. Gotland, it has started. The voltage source converter for HVDC transmission is one of the important factor which we'll be discussing in the coming videos, because that is one of the important concept related to HVDC transmission. So students, let us recall whatever the things that we have discussed in this video. We have started with the basics of HVDC transmission and what is the need for HVDC transmission, why it is required, how transmission is achieved in AC, how transmission is achieved in DC. All these things we have discussed. And next thing is that we have discussed about the early discoveries, and we have discussed about the milestones in the HVDC transmission systems. In Indian scenario, in a global scenario, we have discussed. So that's all about this video.